Welcome back to the channel, geology nerds and disaster enthusiasts. Today, we're diving deep into something that'll blow your mind, literally and figuratively. You see this glassy rock vein? This isn't some fancy art project. This, my friends, is what happens when an earthquake gets so intense, it literally melts solid rock. Yeah, you heard that right. Melts rock. But here's the kicker. The ground shaking you feel during an earthquake? That's just the tip of the iceberg. The real action is happening underground, and it involves temperatures hot enough to melt your favorite minerals. Stick around, because by the end of this video, you'll never think about earthquakes the same way again. Let's get into it. Okay, pop quiz time. When you think earthquake, what do you picture? Buildings swaying, ground cracking, maybe someone's coffee spilling in a dramatic slow-mo. Yeah, same. But here's the thing that absolutely wrecked my brain when I learned it. All that shaking, all that destruction we see in the movies, that's actually just a tiny fraction of an earthquake's total energy. It's like if I told you that when you turn on your car, only 5% of the energy actually moves the wheels, and the other 95% is doing something completely wild that you can't even see. Where does all that missing energy go? Does the Earth just eat it? Does it vanish into the geological void? Spoiler alert, no. It does something way more metal. And today, we're following the money, or rather, the energy, from the moment stress builds up in rocks to the moment that stress turns into something absolutely bonkers. Let's find out where all that energy really goes. All right, I know what you're thinking. Oh, great, a graph. Here we go with the boring science stuff. But wait, this isn't just any graph. This is literally the biography of a rock's worst day ever. Let me walk you through it. Phase 1, the linear elastic region. This is where the rock is like, I got this, I'm a spring, I'm flexible, no problem. All that stress you're putting on it? The rock stores it as elastic energy, like you're winding up a rubber band. Everything's recoverable here. Phase 2, crack initiation. Uh-oh. Now the rock starts forming micro cracks. It's like when you're carrying too many grocery bags and you hear that first little plastic rip. The rock's starting to say, okay, this is getting uncomfortable. Energy is now being permanently lost. Phase 3, peak stress. This is it. This is the rock's absolute limit. Maximum energy stored. It's like that moment right before someone snaps in an argument. Everything's about to go down. And here's the crucial part. That area under the curve? That's the total energy we've pumped into this poor rock. Remember that number. We're going to see where it all ends up. And here it is, the moment. The rock has officially given up. Look at this curve. Immediately after peak stress, boom! The stress just plummets while the strain keeps increasing. This is called strain softening, and it's not a gentle letdown. This is explosive. Think of it like this. You've been bending a stick further and further, and then, snap, it breaks. But unlike a stick, when rocks do this underground, they release energy equivalent to multiple nuclear bombs. All that elastic strain energy that's been building up in the Earth's crust, it's suddenly and violently unleashed. This is what's happening on a fault plane during an earthquake. That rapid stress drop? That's not gradual weakening, that's the Earth basically rage quitting. And the amount of energy released depends on two things: how big the fault area is and how much the stress drops. Bigger fault plus bigger stress drop equals bigger earthquake, equals more screaming seismologists, equals more content for this channel. It's the circle of geological life. Okay, I see some of you glazing over at the equations. Stay with me. This is where it gets interesting, I promise. So we've got this total input energy, let's call it U, which is all the energy we put into deforming the rock. Now, the rock has to do something with all that energy, right? It can't just disappear. Physics doesn't work that way, no matter what your high school teacher lets you get away with. The energy splits into two paths. First, we've got UE, elastic strain energy. This is the stored energy, the dangerous energy, the energy that's just waiting to wreak havoc. It's like potential energy at the top of a roller coaster. Second, we've got UD, dissipated energy. This is energy that's already been lost to irreversible stuff, making new cracks, internal friction, heat. It's gone, spent, used up creating damage inside the rock. Now hold that thought, because we're about to take it to the next level. Okay, here's where it gets really juicy. During an earthquake, we don't care about all the energy. We care about the elastic energy that actually gets released. That's delta UE. This is the energy that was stored up like a coiled spring and then, boom, let loose. Now, this released energy has to go somewhere. It splits into two categories. First, UK, kinetic energy. This is the energy that radiates away from the fault as seismic waves. This is the ground shaking we feel. This is the earthquake as far as most people are concerned. Second, UD prime, additional dissipated energy. This is energy consumed right there at the fault by dynamic processes, primarily frictional heat from rapid sliding and the creation of new rock fractures. And here's the kicker that's going to blow your mind in just a minute. The ratio between these two, between the kinetic energy and the dissipated energy, that ratio holds the secret to an earthquake's true nature. Spoiler alert, it's not what you think, not even close. Now we're getting to the good stuff. Let's break down where the released elastic energy actually goes. First up, ER, the radiated energy. This is the energy that travels away as seismic waves, your P waves, your S waves, the whole shebang. This is what causes the ground shaking. This is what knocks over buildings, what seismometers measure, what we actually feel during an earthquake. This is what most people think the earthquake is. Next, EG, the fracture energy. This is the energy used to actually break the rock, create new crack surfaces, and pulverize rock into that powdery fault gouge you find along fault lines. This is pure destructive energy, creating new surfaces where there weren't any before. And finally, EF, the frictional heat energy. This is the work done against friction as the two sides of the fault slide past each other at high speed. All of this becomes heat. Just heat. So, pop quiz. Which one do you think is the biggest? Most people would say radiated energy, right? The shaking? That's the scary part. Well, buckle up, Buttercup, because you're in for a shock. Okay, are you sitting down? You should be sitting down. Frictional heat energy, 68 to 98%. That's not a typo. That's not a mistake. Most of an earthquake's energy, potentially almost all of it, just becomes heat. Heat from rocks grinding against each other. Fracture energy, less than 1% to 32%. Okay, that's a decent chunk. Makes sense. You gotta break stuff. But here's the kicker. Radiated energy. The ground shaking, the part we actually experience, the part that destroys cities. 1 to 20%. That's it. Let me put this in perspective. Imagine you spend $1,000 on a concert ticket, and only $10 to $200 of that actually goes to the music you hear. The rest? Just friction in the payment processing system. That's earthquakes. The shaking is just the exhaust of the real process happening underground. And get this, that frictional heating can cause flash heating on the fault plane to over 1,000 degrees Celsius. That's hot enough to melt rock. Which brings us to our next question. So you're probably thinking what I was thinking when I first learned this. Okay, cool theory, science person. But if faults are generating temperatures over 1,000 degrees Celsius, hot enough to melt quartz and feldspar, where's the evidence? Where's the melted rock? Shouldn't ancient fault zones be full of, I don't know, fossilized lava or something? And that, my friends, is exactly the right question to ask. Because any good scientific theory needs evidence. We can't just say, yeah, rocks melt underground during earthquakes, without proving it. We need the smoking gun, or rather, the melted gun. So let's go on a field trip. Let's visit some ancient fault zones and see if we can find proof that these extreme temperatures actually occurred. What would that proof even look like? Well, boom! There it is. Look at this beauty. This dark, glassy vein cutting through normal granite? This isn't some volcanic intrusion. This isn't decorative. This, my geology-loving friends, is pseudotachylyte, and it's the closest thing we have to a fossilized earthquake. Say that 5 times fast. Pseudotachylyte. Pseudotachylyte. Fun word, right? Here's what makes this absolutely incredible. This glassy rock was formed by the direct solidification of friction-induced melt. Not volcanic melt, friction melt. 2 rocks rubbing together so violently, so rapidly, that they literally welded themselves together with their own melted bodies. It's like if you rubbed your hands together so fast that your skin melted and re-solidified into glass. Horrifying mental image? Yes. Accurate analogy? Also yes. This is a preserved record of an actual earthquake slip event. This is a fossilized earthquake. How cool is that? You're looking at violence frozen in time. All right, let's break down the 3 steps to melting rock with friction. Yes, there's a recipe for this. No, you cannot try this at home. Step 1. During an earthquake, fault blocks move at speeds of 1 to 10 meters per second. That might not sound super fast. It's like jogging speed. But remember, these are massive blocks of rock we're talking about. Think about the friction involved in sliding a mountain past another mountain at 10 meters per second. Yeah. Step 2. That intense shear stress generates heat much faster than it can conduct away. It's like friction welding metal. You're creating heat faster than it can dissipate. The temperature on the fault surface spikes over 1,000 degrees Celsius. For reference, your oven at home maxes out around 260 degrees Celsius. We're talking 4 times that. On rocks, underground. Step 3. A thin layer of melt forms between the rock surfaces. It's like the world's most violent buttering of toast. And then, here's the crucial part. When the slip stops, that melt cools and quenches almost instantly, forming a glassy vein of pseudotachylyte. It happens so fast that minerals don't have time to form proper crystals. They just freeze into glass. And that's how you get evidence of ancient earthquakes literally written in melted stone. Now here's where pseudotachylyte becomes more than just cool-looking rocks. It becomes a geological calorimeter, a thermometer for ancient earthquakes. Let me explain how we read this rocky crime scene. Thermal modeling. The thickness of the pseudotachylyte vein is directly related to how much frictional work was done. Thicker vein equals more energy equals bigger earthquake. Using heat conduction models, basically fancy math about how heat spreads through rock, scientists can back-calculate the shear stress and total slip of the ancient earthquake. We can literally measure a 100-million-year-old earthquake's magnitude from the thickness of glassy rock it left behind. How insane is that? Microstructural analysis. Now we zoom in with microscopes and look at the internal texture. Which minerals melted? Biotite melts before quartz. So if we see melted quartz, we know temperatures exceeded 1,000 degrees Celsius. Suspended rock fragments tell us how much crushing happened alongside the melting. Look at this microscopic view. That glassy matrix? That's quenched melt. That mineral clast? That's a chunk of host rock that didn't quite melt. It just got caught in the glass, like a terrible geological jello mold. We're literally doing forensic science on ancient earthquakes. This is CSI Fault Zone Edition. So what have we learned? What does the existence of pseudotachylyte actually prove about earthquake physics? 2 massive things. Key insight number 1. Dissipation dominance confirmed. The widespread existence of frictional melt is tangible, hold it in your hands, proof that the energy required to heat and melt rock is a dominant part of the energy release. That energy budget pie chart we looked at earlier? It's not theoretical, it's real. Frictional heat dominates. The ground shaking is just the side effect. Key insight number 2. Dynamic weakening explained. Here's where it gets even cooler. That melt we just created? It acts as a lubricant. Think about it. You've got 2 massive rock surfaces grinding against each other, and suddenly there's a layer of molten rock between them. The friction dramatically drops, which allows the fault to slip farther and faster. This is called dynamic weakening, and it's crucial for explaining how faults can move so far, so fast during major earthquakes. It also solves the heat flow paradox on major faults like the San Andreas. Scientists were puzzled why these faults don't show massive heat flow at the surface if so much frictional heating is happening. Answer? The melt lubricates the fault, lowering friction, reducing continued heating. The system self-regulates. This is elegant physics written in stone. And here we are, at the end of our journey from theory to proof. Let's recap this beautiful progression. We started with an abstract stress-strain curve, just a line on a graph representing forces in the crust. Pure theory. That theory predicted a specific energy budget. Most energy goes to frictional heat, not ground shaking. Bold prediction. The mechanism explained how. Rapid slip generates extreme temperatures that melt rock. Testable hypothesis. And the proof? The proof is lying on fault zones around the world. Dark, glassy pseudotachylyte veins that serve as permanent records of ancient earthquakes.